Welcome to Engineering Simplified. Have you ever wondered how an air conditioner can move more energy as heat than it actually consumes as electricity? It sounds like it breaks the laws of physics, but it doesn't. The answer lies in the refrigeration cycle. Let's break it down. Every basic refrigeration system, whether it's a fridge, an air conditioner, or a chiller, moves heat using the same four components: the compressor, the condenser, the expansion valve, and the evaporator, all connected in a continuous loop. The cycle starts at the compressor. It takes in low-pressure refrigerant gas and compresses it, which raises both its pressure and its temperature significantly, turning it into a hot, high-pressure gas ready to give up that heat. That hot gas then flows into the condenser, where it releases heat to the surrounding air or water. As it loses heat, the refrigerant condenses from a gas into a high-pressure liquid, usually subcooled a few degrees to guarantee it's fully liquid. Next, that high-pressure liquid passes through the expansion valve, which drops its pressure suddenly. That pressure drop causes some of the refrigerant to flash evaporate, cooling the remaining liquid to a very low temperature. Finally, that cold, low-pressure refrigerant enters the evaporator, where it absorbs heat from whatever needs cooling, boiling back into a low-pressure gas. That gas then returns to the compressor, and the cycle repeats. If you're enjoying this, like, comment and subscribe, and check out the other Engineering Simplified playlists. Now that we understand the cycle, how do we measure how efficiently it actually works? That's where COP, or coefficient of performance, comes in. COP is simply the ratio of useful heating or cooling output to the electrical energy put into the compressor. Unlike a car engine or a heater, a refrigeration cycle isn't creating energy. It's moving existing heat, so its COP can be, and usually is, greater than 1. That's not free energy either. The compressor's work doesn't vanish. It joins the heat absorbed at the evaporator, and the total leaves through the condenser as rejected heat. COP just describes how much heat gets moved for every unit of work you put in. For a cooling system, COP equals the cooling output in kilowatts divided by the compressor's power input in kilowatts. For a heat pump used for heating, it's the heat delivered divided by that same power input, and it's always roughly 1 higher than the cooling COP, since the compressor's own work becomes part of the delivered heat. Say a chiller removes 10 kilowatts of heat from a building's water loop, while its compressor draws 2.5 kilowatts of electrical power. COP equals 10 divided by 2.5, which gives a COP of 4. That means for every 1 kilowatt of electricity supplied, the system is moving 4 kilowatts of heat. A higher COP means a more efficient system, using less electricity to move the same amount of heat. Typical air conditioners run somewhere between COP 3 and COP 4, while well-designed chillers can reach COP 5 or higher under good conditions. The common mistake is treating COP as a fixed number stamped on a nameplate. COP actually changes with operating conditions. A system working against a large temperature difference, like cooling a building on a very hot day, has to work harder and its COP drops. Ignore that and you'll size equipment or estimate running costs using a COP that only applies under ideal lab conditions, leaving you with a system that uses far more electricity than expected once summer heat actually arrives. So remember, the refrigeration cycle moves heat through 4 stages: compression, condensation, expansion, and evaporation. And COP tells you how efficiently that cycle moves heat for the electrical energy you put in. Understanding both the cycle and its COP is exactly what lets engineers select the right equipment and predict how much energy a cooling system will really use. Drop a like, comment the topic you'd like to see explained next, and subscribe. It genuinely helps this channel grow. See you in the next Engineering Simplified video.